Magnetization of material. Matter is made up of atoms, which are made up of electrons and a nucleus. The electrons revolve around the nucleus in a circular orbit, just as current carrying loop constitutes magnetic dipole moment. Electrons moving in these orbits also constitute magnetic dipole moment. Beside the orbital's motion, the electrons also have a spin motion along an axis similar to Earth's rotation. This spin also constitutes a magnetic moment which has a fixed magnitude of 9.285 into 10 to the power minus 24 joule per Tesla. The nucleus has a magnetic moment, but it is very negligible when compared to that of electrons. The resultant magnetic moment of an atom is the vector sum of all the magnetic moments in an atom. The resultant magnetic moment of an atom depends on the number of unpaired electrons in the atom. Some atom contains paired electrons in all their orbitals. For the sake of understanding, let us consider helium atom, which contains only one pair of electrons. The paired electrons have orbital motion and spin opposite to each other. Due to this, the magnetic moment of paired electrons have some magnitude but have opposite direction. The magnetic moments would then cancel each other out and the resultant magnetic moment will be zero. Some elements have unpaired electrons in their orbitals. In such atoms, the magnetic moment of the unpaired electron is not cancelled due to the absence of the paired electron. Due to this, the resultant magnetic moment in the atom will not be equal to zero. The atom behaves like a tiny bar magnet. Every material consists more than one atom. Generally, the magnetic moments of these atoms are randomly oriented and the net dipole moment of the material is zero. However, when the material is placed in external magnetic field, the magnetic moments of these atoms tend to align themselves to the magnetic field and develop a net magnetic moment. Now let's discuss about an important term called magnetization, also called as intensity of magnetization. When a magnetic material is subject to magnetizing force, the material becomes magnetized and develops a net magnetic moment that is not equal to zero. The intensity of magnetization helps us to measure to what extent the material is magnetized. It is defined as magnetic moment developed per unit volume of the material placed in the magnetizing field. Magnetization is equal to magnetic moment by volume. Magnetization is a vector quantity and its SI unit is ampere per meter. Before continuing the topic, let us learn about few terms. Magnetic flux density. Magnetic flux density is the measure of the number of magnetic field lines passing through the unit area normally. It is also known as magnetic field. It is a vector quantity and it is denoted by symbol vector B. Diamagnetism. In diamagnetic materials, the atoms contain fully filled paired electron orbitals. The vector sum of magnetic dipoles of all orbital electrons is zero. Hence, no permanent magnetism is found in such substances. At atomic level, the electrons revolve around the nucleus due to the centripetal force acting on it that is directed towards the center. Also, the velocity of the electron depends on the magnitude of centripetal force acting on it. When the diamagnetic material is placed in an external magnetic field, each of the orbital electrons experience a mechanical force called Lorentz force. The direction of the Lorentz force depends upon whether the electron is moving in clockwise direction or anti-clockwise direction. If the electron is moving in anti-clockwise direction, the Lorentz force acting on the electron will be in radially outward direction. Since these two forces are acting on the same line and in opposite direction, the effective centripetal force acting on the electron will decrease. Due to this, the velocity of the electron will also decrease. Hence, Due to decrease in velocity, the magnetic dipole moment of the electron will decrease. On the other hand, in the case of electron which is moving in clockwise direction, the Lorentz force acting on the electron will be radially inward direction. Since these two forces are acting on the same line and in same direction, the effective centripetal force acting on the electron will increase. Due to this, the velocity of the electron will also increase. Due to increase in velocity, the magnetic dipole moment of the electron will increase. Similarly, all the electrons in various orbits experienced a change in magnetic moment. Some become short and some become long. Due to this, the atom develops a net magnetic moment in the direction opposite to that of the applied field. Paramagnetic materials. The atoms of paramagnetic materials have unpaired electrons in their orbits, due to which they have a permanent dipole moment. In the absence of external magnetic field, the magnetic moments of atoms are randomly oriented and the net dipole moment of such material is zero. When an external magnetic field is applied, the magnetic dipoles experiences a torque and tries to align in the direction of the applied magnetic field. At the same time, the thermal energy of the material opposes the alignment and tries to keep the dipoles in random orientation. Due to the opposing factors, only small number of dipoles align in the direction of magnetic field and the magnetization intensity of that material will become non-zero. The magnetization of paramagnetic material depends on two major factors: temperature and external magnetic field. As the magnetic field increases, more number of dipoles can overcome the thermal energy and align with the magnetic field. The magnetization of the material increases. When temperature of the material is decreased, the thermal energy of the material decreases. Now, more number of dipoles can overcome this lower thermal energy and align with magnetic field. The magnetization increases. Again, if the temperature is increased, the thermal energy of the material increases. Now, some of the dipoles that already were aligned experience higher thermal energy and become randomly oriented. The magnetization decreases. Now, instead of external magnetic field B, it would be appropriate to use the term magnetic intensity H, which is the actual source of magnetic field. It is given by H is equal to B by mu. Therefore, we can say that the intensity of magnetization of paramagnetic materials is directly proportional to the applied magnetic intensity and inversely proportional to the absolute temperature. M is proportional to H by T. Removing the proportionality sign, the equation can be written as M is equal to C into H by T. Here, the constant of proportionality C is called Curie constant. Now let us discuss about an important term in magnetism called magnetic susceptibility. The magnetic susceptibility of material indicates how much a substance becomes magnetized when it is placed in an external magnetic field. It is denoted by this symbol, chi m. Magnetic susceptibility of material is defined as the ratio of intensity of magnetization m to the applied magnetizing force H. Chi m is equal to m by H. Since H and m have same units, the magnetic susceptibility is a unitless quantity. Now, if we consider this relation, m is proportional to H by T. This relation can be rewritten as m by H is proportional to 1 by T. Now let us replace m by h by magnetic susceptibility. Now, from this relation, we can say that magnetic susceptibility of a paramagnetic material is inversely proportional to absolute temperature. This relation is called Curie law in magnetism. The Curie law has certain limitation. Let us discuss about it. Earlier we have learned that the magnetization of paramagnetic material increases with increase in applied field. The magnetization also increases when the temperature of the paramagnetic material decreases. In both of these cases, after a particular point, the magnetization does not increase even after increase in field or decrease in temperature. This is called saturation of magnetization. At saturation, almost all the dipoles in the material are aligned with the magnetic field. It is to be noted that Curie's law is applicable only when the magnetization of the material is far away from its saturation. Properties of paramagnetic materials. 1. A paramagnetic material is very weakly attracted by a strong magnetic field. 2. When a paramagnetic substance is placed in external magnetic field, some of the dipoles inside the material align in the direction of magnetic field. The material is weakly magnetized and acts as very weak bar magnet with north and south pole. Now, the magnetic field lines produced by this material are in the direction of external magnetic field inside the material, and the field lines are opposite to external magnetic field outside the material. The resultant magnetic field will look something like this. The magnetic field here looks as if they prefer to pass through the paramagnetic material rather than air. The magnetic field B inside the conductor is more than the external magnetic field B. 3. Since the magnetic field B inside the material is greater than the external magnetic field B naught, the relative permeability mu r is equal to B by B naught is always greater than 1. The magnetic susceptibility chi m of paramagnetic material varies inversely with absolute temperature. That is, chi m is proportional to 1 by T. The magnetic susceptibility of paramagnetic materials has a small positive value. 4. When a paramagnetic material in the shape of a rod is suspended freely in strong uniform magnetic field, the rod experiences a force and comes to rest in such a way that its longest axis is along the direction of the magnetic field. Ferromagnetism. In ferromagnetic materials, the atoms contain more number of unpaired electrons. For example, iron contains 4 unpaired electrons. Due to this, the net dipole moment of an individual atom is more compared to atoms in paramagnets. The dipole moment of one electron strongly interact with the dipole moment of the neighboring atoms and align themselves in a common direction. This small group of atoms with dipole moments in same direction is called a domain. A ferromagnetic material as a whole is made up of very large number of such domains. In the absence of external magnetic field, the dipole moment of different domains are oriented randomly in different directions. The dipole moment of one domain cancels the dipole moment of other domains, so that the net magnetic moment of the entire material is 0. In the presence of external magnetic field, the domain starts to align in the direction of applied field. The magnetization intensity becomes non-zero. Currently, since the external magnetic field is weak, only one domain has aligned with the external magnetic field. As field gets stronger and stronger, more and more number of domains start aligning with the external magnetic field. The magnetization intensity goes on increasing. Then, for a particular strong magnetic field, the magnetic moments of all the domains get aligned in the direction of magnetic field. Now, the material is at its ultimate stage of magnetization. Now, magnetization does not increase even if the external magnetic field is increased. This stage is also called saturation of magnetization. Just like paramagnetic materials, ferromagnetic materials are also influenced by temperature. When a ferromagnetic material is heated due to thermal energy, the dipole moments within the domain start coming out of the alignment and become random. The randomization goes on increasing. Then, at a particular temperature, the domain structure becomes completely destroyed and the ferromagnetic substance becomes paramagnetic substance. This particular point is called Curie point. Curie point or Curie temperature is defined as the temperature at which a ferromagnetic material becomes paramagnetic material. The Curie temperature of iron is 1043 Kelvin and for cobalt is 1394 Kelvin.